Hello and welcome to Geos1110, and this is practical 1 of the course, and this is obviously the first practical in module 1 as well, which is about the solid Earth. Now in this particular practical we're going to be talking about deep time and the history of the Earth, so I'm going to take you for a walk through the geological timescale to try and appreciate how Earth has changed through time, but exactly how long geological history goes for. Now, to help with this, some time ago we were involved with the Macquarie Timelines app, which is available on the Google Play Store there, or alternatively you can use a web browser version of it, which is available at timelines.science.mq.edu.au. Now, if you ever wanted to go back and refer to any of the content there at any time, you can go back to that link and it will show you the timelines. You'll be able to find the Earth's timeline there, and a lot of content as well, and images linked to different parts in Earth's evolution. So the practical normally is divided into two parts. For the internals at the start of the semester, I spend a bit of time going through the unit guide webpage and etc. etc. I'm going to assume that that's okay for most of the people listening to this at this point, and I'll post some information about that component of it on the iLearn page. But what we're going to do now is actually look at the timeline app itself and do a walk through Wally's walk from the start to the end, and get an idea of when different periods in geological history occurred, how the Earth changed through that walk through geological time. We're going to start at the origin of the solar system and walk through the geological record all the way to the present. Now, as we do so, there are some questions to do as part of this prac as well. Now, I'll generally blurt the answers out as we're walking along the timeline, but do keep these questions in the back of your mind as you're listening, and try them, fill them out as you go, and answer these in sequence. So they're fairly standard, and I think the sections they apply to should be reasonably obvious, but have a crack at answering these questions as we go for our stroll, and then right at the end I've given you the task of creating your own timeline on this little ruler here. So 1 centimeter equals about 460 million years, and the entire ruler then would be the entire geological history of the Earth, and I want you to note in some of the big events in Earth's history there. Right, so without further ado, let's jump to the timeline app. Okay, so this is an example of the online version of the Macquarie Timeline app. It's available if you go to timelines.science.mq.edu.au. Now, it looks something like this, and within it at the top you can select what timeline you're interested in. We're looking at the Earth, and then you can select discrete events in the history of the Earth and see where they appear at the timeline. So we start at the birth of the solar system, which is the start of Wally's walk in the intersection with Research Park Drive, all the way over here. Bit of construction going on Innovation Road right now, and then we're going to walk the entire way past here, past molecular sciences, past the biology building here. The teaching labs are in this building here. We're going to move past the earth science offices are mostly in there. This is a big construction zone at the moment. We're going to get past that. Here's the Muse building, which some of you might know in here. Little coffee cart tucked away in there. Then we reach this intersection. There's a little grassy area down here. This is the gym over there. And then as we move through here, we're going to get to more and more recent time. We're in the Proterozoic now, a lot of events occurring. And the present day then would be down here, right outside the Ancient History Museum. So that's the timeline itself, and you'll be able to follow events in the timeline. If you click on them, it'll show you what event it is up here. And if you have a look down here, they'll actually tell you a little bit about what was going on during some of those events. So I'll be referring to both the timeline here and some of the imagery we have during the walk itself, but this is where you find it.
Well, welcome to the start of Wally's Walk anyway. We're at the corner of Wally's Walk and Research Park Drive here, and on the Macquarie timeline, this is the start of the solar system. So we're at 4.56 billion years ago at this point. There are no planets, there is no sun. We're just a swirling cloud of gas and dust in a stellar nursery environment where we have a lot of new young stars forming, and these things are starting to condense, and the gas cloud that's to become the solar system is about to condense and form the proto-sun and the disk of planets around it. This was a particularly violent environment, probably even noisier than this construction site we're at right now. So let's move forward quickly and we'll see what happens next. So we stop again, literally right about here, because between then going from a cloud of gas and dust into the first solids forming, they formed about 1 million years or so into the solar system's history. Now, the very earliest material to form in the solar system actually formed from the dust in the gas cloud itself. And these little grains of dust got melted. We think they got melted by big shock waves moving through the system as the planets were starting to form. And from those little droplets of molten dust, they crystallize and form these tiny little millimeter scale little balls we call chondrules. So they're little spherical bits of materials, they're little bits of mineral that are crystallized inwards out of molten droplets. And those chondrules stuck together to form a very primitive sort of meteorite called a chondrite. And this is what I'm holding here. This is defined as an ordinary chondrite. It's a very simple form without too much organic material in it. But this was what the earliest solar system looked like. This was some of the earliest solids that actually formed directly from the dust and gas of the protosolar nebula. So at this point, we've had a gas cloud condense down, the protosun has started to shine, it's starting to blow a lot of that gas away. These chondrules and the other solid material are in a race now to build planets up before all the gas that they have to build planets from gets blown out of the solar system completely. So, the next step, planetary formation, also happens extraordinarily fast. And if we zoom forward a little bit, just to here, we've actually jumped from forming the first solids in the solar system to actually forming the first protoplanets and then planetary systems here. So at this point, as those little drops of chondrules pile together and form bigger and bigger bodies, they get more and more sticking. Eventually gravity becomes important. They start pulling more bodies together to form increasingly larger sizes. By the time you get up to bodies around 100 kilometers or so across, they're getting big enough. You've moved from protoplanets to planetesimals, they're getting big enough to start melting in the interior. And when that happens, when you start melting these chondrules, you release metal, you release basically magma, and the metal sinks to the cores, the interior of these nascent planets, and the magma and the crystals are formed from the magma float upwards. So you end up with a differentiation of these very primitive bodies into a rocky exterior, which was originally magma, and then a molten metal interior, which then crystallizes out to form a solid core. And in the meteorite collection now, we find a whole bunch of meteorites known as iron meteorites, of which this is one. This is from Wolf Creek in Western Australia. I did some field work there when I was a PhD student. This is a solid chunk of iron that formed in a core of a very tiny little protoplanet while it was still forming at the dawn of the solar system. That protoplanet got hit. There were hundreds of little protoplanets floating around at that time, not many of which were stable, so they collided in with each other. Many of them got destroyed, and some of those that got destroyed, we see the preserved fragments of their cores and planetary bodies still in the asteroid belt today. So a lot of our iron meteorites are sourced from the asteroid belt, and they represent the shattered remnants of planets that never got a chance to grow to full size. Now, of the ones that did grow to full size, they then grew very quickly. So if we move forward to about here, we're now about 10 million years into the solar system history at this point, and we've started to form the earliest planets. Jupiter, by this point, has been a large planet. It's been around for quite some time. The gas of the disk has been blown out now by the star, and what we're left with are some of the planets that are beginning to look a lot like what they look like today. This little fragment here is a fragment of Mars. This is a sample of the Martian crust. It's a volcanic rock, and it's called a shergotite, which is named after where the meteorite type was first found. So, it's made up of tiny little globules of spherical material from which we can tell this is a completely different planetary body than the Earth. One of the first ways we worked out these type of meteorites were from Mars. There's many volcanic rock trap little bubbles of the atmosphere inside them as they form. And some of these early Martian meteorites, which were discovered in places like Antarctica and the Sahara, in the case of this little guy, they have these preserved bubbles in them. And when the composition of those bubbles was analysed, it was found to be 96% carbon dioxide, trace amounts of nitrogen, and noble gases like krypton and argon, and in exact percentages that matched one-to-one the atmosphere that we see from Mars from the Viking missions today. Right, so this was a very violent time. There was a lot of impacting going on. This was shaping the face of the planet. And this continued for quite some time. So we're going to move ahead now and see what effect that had on the Earth just up here. About 100 million years into the solar system's history. So we've had a lot of the early planets have formed. At this point, Earth is about 90% of its current size. But there's an awful lot more planetary bodies around at this time than exist today. Now, many of them are in unstable orbits. We think in around Mercury, there may have been up to 9 or Mercury-sized planets close to the Sun. Most of them got destroyed. In the case of the Earth survived a lot of that initial bombardment and collisions, but it didn't survive unscathed. This is a fragment of the Moon. So this got blasted off the Moon by a meteorite and was found in the Saharan Desert in northwest Africa in Algeria. And you can see on it, it's got this dark material, which is part of the mare. So when you look at the Moon and you see its near side, and you see that kind of dark material filling in some of the craters, that's all basalt. So they're fairly recent flows, i.e. they're still 3 billion years ago. But that stuff formed volcanically as the Moon was still geologically young. Some of these little white crystals you're seeing here, though, are a type of feldspar. Now, these are more interesting. How they formed was these feldspars make up 80% of the surface of the Moon. They're a really weird rock type that we don't see much on the surface of the Earth at all. And these feldspars originally grew out of a magma ocean on the Moon. So the entire Moon started its life molten. And as it started to cool down, it started to crystallize some different crystal grains out. Some were heavy and sunk, but some, like the feldspars, were actually light. And these floated to the top of the magma ocean and formed a scum at the top of the ocean. And in fact, are still there today. So 80% of the lunar crust is the lunar highlands, and it's nearly all made out of this white material, anorthosite. So this all came out of the Apollo missions back in the 60s and 70s. And the question has always been, well, how did the Moon start life so hot? And the story that evolved from Apollo was that at this time the Earth was hit by a giant impactor, something the size of Mars perhaps. It came in, hit the Earth at a glancing blow, and would have vaporized huge amounts of the Earth and itself. The rest of what was left over was molten, and out of that spinning disk of molten vaporized rock, the Moon eventually coalesced, and then the Earth started life as a molten magma ocean. Now, most of the evidence for that on the Earth has been destroyed. The Earth's very geologically active, but it's still preserved on the Moon because the Moon hasn't had a very deep geological history like the Earth, and we see evidence of this very earliest process still in the lunar rocks we have today. Right, let's move ahead now. Now, much of what we're going to talk about here are in an epoch known as the Hadean. And the Hadean itself is known as Earth's geological dark age. We think it was fiery, we think it was violent, but one of the problems is we have no geological record of that. Earth today has plate tectonics, very successfully recycles its crust, and so there's very little preserved from this earliest part of the Hadean. Very little, but there is something. I'm going to show you right from about up here what that something looks like. Right, so from about here, we're around 4.3 to 4.4 billion years ago at this point. So still ancient, still in the Hadean, but as I mentioned, we have no rocks surviving on the surface of the Earth from this period. There was a lot of meteorite bombardment that destroyed a lot of the early crust. There was a lot of volcanism, and later on there's been 4 billion years of plate tectonic activity. So those factors combined mean there's just nothing that's left from this time, except these little grains of something we call zircon. Now, zircon is an unbelievably tough little crystal. It grows in rocks like granite, but when a granite erodes away and all the crystals start tumbling downstream, some of the tough ones like quartz eventually form sands, but even tougher than quartz is zircon. This is a big piece of a zircon just here, and these are much smaller pieces of zircon, but these are so tough they survive that process of weathering out of a rock, tumbling down in a surface environment, being dropped into a sandstone, weathering out of that, tumbling down and being preserved. And in fact, we see zircons, and these are from much younger rocks than this, sometime around in the Archean, so maybe 1 billion years later. But the zircons from those younger rocks, which we find in a place called Jack Hills in Western Australia, actually are from a rock much, much older than that sandstone we found in. And some of those zircons actually formed during this interval, during this Hadean period. So the oldest of them that we have are up to around 4.4 billion years old. So these are our only record of what happened on the Earth from that early Hadean period. And they tell us some interesting things. The first is that the zircons themselves grew out of something like a granite. So immediately we had rocks very similar to today, things like granites forming at this time, which is interesting in and of itself because continental material is made up of a lot of granite. So we had something that looked like present-day continents existing, at least in some form, around in the early Hadean. But the big story to come out of the zircons is when we actually looked at the chemistry of the zircons, and in particular the oxygen, they tell us something about the environment the granite was in as well. And it turns out that granite was interacting with water at the surface. So the granites formed in an environment where there was liquid-water interaction. And that's what we detect from the chemistry of these little zircon grains, which is interesting because at this point not only do we have something that looked like continents, but we had liquid water around, and people have made the argument we had oceans as well. And perhaps the Earth during the Hadean wasn't quite so horrific as we once thought it might have been. Right, now let's move on now to the next period of Earth's history. So we're going to take a little walk just up to the end here. Alright, so we're just about to exit the Hadean, so this period of planet building, intense bombardment, volcanism, and as we exit this, we're coming up to about 4 billion years ago, just up here. So, the earliest period of Earth's history, the hellish period of Earth's history, and the geological dark ages are just about to end. So right now, we're at the boundary of what's known as the Hadean and Archean. And this marks the beginning of geology because right here we find the Earth's oldest rocks. This guy here is a metamorphic rock. It's called a gneiss, and you can see this metamorphic layering of different minerals that formed in it. This rock was under really high temperatures and pressures and got squished and flowed like toothpaste. Now, this particular gneiss has a lot of zircons on it, and you can date these zircons using the amount of uranium in them. Now, uranium's radioactive and it decays through time. So if you know, eventually it ends up lead, but if you know how much uranium you start with and how much you're left with, you can work out how old the crystals that contain that uranium are. When that's been done for these particular rocks, turns out that this particular rock, this gneiss, is about 4 billion years old. So this is the Acasta gneiss. This is from a place in northern Canada. Really little outcrop of rock, not much of it, very hard to get to. Horrible, horrible little bitey insects up there in the summer. But this is the start of geology, really. Now, there's not a lot else we can tell about this rock. It's been heavily metamorphosed, so what the surface environment was like when this rock formed is fairly unclear. Now, we do have another example of perhaps another candidate for Earth's oldest rock, which also comes, coincidentally, from Canada, which is this guy here. This is a rock we call a greenstone. and it has an Inuit name. It's from Quebec, northern Quebec in Canada, the Nuapatak greenstone. And if anyone here knows Inuit properly, I'm sorry, I just massacred that. But this rock, we don't have any good zircons in it. We don't have a very good age for the uranium in it. So we can't tell exactly how old it is. But what we can tell is we look at other systems, other isotopes that might give us a hint of the age. And when that's been done for this rock, the suggestion is that this rock may actually be older than 4 billion years old. It may actually be up to perhaps maybe 4.2 billion years old. So this is a running candidate for one of the oldest rocks in the world, but it's contentious at the moment. It only has this modeled age, which means that it's not as definite as the acastanite. Either way, here's where it all begins. The geological record has started, and we have it now a bit of an indication of what's happening through time. Now, I mentioned the geological record starts. One of the reasons why we don't have much of one in the Hadean was meteorite impacting. Now, that was really important early on. It's how we built planets. It kind of tailed off for a little bit there, but now it's about to get real again, just up here. So right up here, we're now into a period known as the Archean. So really ancient rocks. They seem to be forming in regimes unlike anything we see in modern geology today. So at this particular point, though, right here, we're at about 3.8 billion years ago. And what we see at this time, not on the Earth, there's not much rock exposed, but on the Moon at least, is what we see on the Moon at least, is a lot of craters that actually formed at that time. Now these craters have been dated, so we have samples of them from Apollo, and we can tell exactly when they formed by using dating techniques like uranium-lead. And a lot of the craters on the Moon are around this period, about 3.8 to 3.9 billion years ago. Now, that's interesting because we had a lot of impacting earlier on, and then we seem to have a lot of impacting right now. This has been called an event known as the late heavy bombardment. Now, the reality of it has been argued quite a bit in the literature, and people argue about the dates. They actually think perhaps there's an older age to the late heavy bombardment now. But the upshot of this is these style of impacts, whatever we see on the Moon from the late heavy bombardment, would have been multiplied by a factor of 10 when they hit the Earth. The Earth's much bigger, would have had bigger impactors hitting it, they would have been moving faster. So the Earth would have absolutely been smashed during this period. In fact, the impact size we're talking about are not just dinosaur killers, they're planet killers. The energy of these impacts is enough to vaporize all of Earth's oceans. So we're talking about a situation where we're periodically sterilizing the planet due to these impacts forming. So this, as you can imagine, probably not the best environment for life. But yet, we're not far off the earliest evidence of life here. Now, when we look at the universal tree of life, something really particular stands out. Whilst these impact events may have vaporized the entire oceans, they may not have had much of an effect underneath the rock surface themselves. So if you could exist inside the rocks, you're probably fairly immune to these style of impacting events. There are an awful lot of bacteria, particularly archaea, which are a type of life related to bacteria, related to us, they're a separate kingdom. But these guys are extremophiles. They love living in extreme environments, extreme heat, extreme acidity. They eat weird things, create methane, all that sort of stuff. But the particular earliest formed ones, so when you actually look at the tree of life and you look at the genomes of all these different bacteria and archaea and work out what organisms are very closest to that core of the tree of life, the root of the tree of life, where it all started, the most primitive organisms in the world, they are all extremophiles. And in fact, they're all hyperthermophiles. They love living in heat. So the earliest thing we can see today to a universal common ancestor seem to have been something that was adapted to living in a hot environment. Now, whether or not that related to what the Earth was going through at this point is speculative. But certainly, if anything made it through this sort of environment, these sterilizing impact events, it had to be able to handle the temperatures and probably survive deep underground. Now, if we go a little forward now, we're about to see life really kick off in seriousness. Right, now in geology, we like our origin stories. We like to be able to put our finger on something and say, here's where it all began, here's where it started. And it's hard with an imperfect geological record, but if you had to put your finger on one point of geological history and say, here is where life began, it may as well be here. At this time, we're at 3.5 billion years ago in the Archean period, and what we see for the first time are fossils. We see definite fossils of a weird type of organism called stromatolites. If you've ever been to Shark Bay, you may have seen these because stromatolites are still around today. They're a form of blue-green algae, and they form these algal mats that grow up towards the sun, and then you get a bit of sediment coming over when the high tide comes in, and they grow up a little bit more. Now, being just an algal mat, they're very susceptible to something like a snail coming over and just eating them. So they tend to survive in niche environments today. In Shark Bay, it's very salty, so you don't get too much snail predation. But you get these slow domes growing in much the same way as they seem to have grown 3.5 billion years ago. And we see these structures in the Pilbara in Western Australia that date to 3.5 billion years old. So these are fairly complex structures. They tell us two things. One is that cyanobacteria, blue-green algae, have been around a long time, and it's been a very successful way of life. They've survived fairly unchanged since about 3.5 billion years ago. They're also fairly mature at this point, which means life had already started before this and evolved into these niches, evolved into an ecosystem by 3.5 billion years ago. So the origin of life is shrouded in the Archean period that we've just walked through. The other interesting thing, though, is blue-green algae photosynthesize. In fact, the biological mechanism for photosynthesis that trees use was actually stolen from earlier bacteria, including blue-green algae. So these are the original photosynthesizers. In fact, probably they innovated to form oxygen photosynthesis from around this period. Now, the early atmosphere didn't have oxygen in it. Most of the oxygen in the atmosphere came originally from life, photosynthesis. At this point, there hadn't been enough life, long enough or enough photosynthesis to dominate the atmosphere. The atmosphere is primarily volcanic gases. So carbon dioxide, bits of methane, maybe a little bit of nitrogen, but a very different atmosphere to what we have today, and completely unbreathable for us because there's absolutely no oxygen in it at all. But this is the start of life's story in the geological record now, 3.5 billion years ago. Let's move forward a little bit more to the start of modern geology. Right, I've got nothing to show you here, but the interesting thing about this period is that if you took an average of when most people think plate tectonics started, it probably started now. Now, plate tectonics these days is modern geology. It defines how the planet behaves, how you build mountains, how you create new crust, construct old crust. It is the modern geological cycle. It has very distinctive rocks that have formed in certain environments, and prior to this, we don't tend to see many indicators of anything you call plate tectonics. Most people would argue that it started to initiate sometime around 3 billion years ago, around now. So this is the start of the modern geological cycle. Now, this is hugely contentious. Some people have said it didn't start until 700 million years ago. Some people have argued it started back in the Hadean. So there's quite a difference of opinion over it. And of course, this is largely due to people interpreting different portions of the geological record in different ways. And the geological record, of course, is very imperfect for these ancient periods. But if you took a consensus view now on when plate tectonics are likely to have started, sometime around 3.5 billion years ago is not a bad estimate. Alright, we're going to start jumping through time reasonably fast now because we're going to cover huge swaths. Right, so we're at about 2.9 billion years ago now. Now, one of the interesting things about this period is we see the first evidence of ice on the planet. And we'll have a look at some better indicators for ice later on when we actually freeze the entire planet. But for now, the interesting part here is that We didn't see more ice prior to this in the geological record. At this point in the geological record, we have ripples. We see the evidence of liquid water on the surface of the Earth. We have things like liquid water all the way back in the Hadean. And yet this is fairly remarkable because for the case of the Earth, the Sun is quite different during this period than it is now. Now, most astrophysical models actually have the Sun starting life fairly faint, and it actually grows brighter through time. Eventually it'll end up a red giant, and it'll cover the Earth's orbit, and the Earth will die a fiery death. But before we get to that in 5 billion years' time, at least here, the Sun is about 70% less bright during this period than it is today. Now this is a huge problem for the Earth, because 70% less radiation coming in means it's very hard to maintain surface temperatures. I mean, if we had 70% less sunlight coming in now, we'd be freezing all the time. The whole Earth would freeze over. And in fact, this is the main problem with the early Earth. It's known as the faint young sun paradox. The amount of radiation coming in from the sun, the Earth should have frozen over for most of this early period. But it didn't. And the reason it didn't was largely due to the volcanic atmosphere that we had, large amounts of CO2 coming out from volcanoes. Now that started to wane for the first time at this point. We see things like ice forming just for a little snippet here, but that's about to change because volcanoes are going to come back in force in just a little while. Brutally sunny here today. I might go over here to bikes. It's what I normally do.
So the system may have finished by the time you get to the end.
It's the full one in very place. Alright. Okay, we're good. So at this time, we're at about 2.7 billion years ago now, so not quite halfway through our journey through the history of the Earth, but approaching the end of the Archean. Now, the Earth had started to show signs of cooling down a little while ago. That stopped now, and then we had what effectively is one of the largest outpourings of volcanism that the Earth has ever seen, right around this period of about 2.7 billion years ago. Every exposed landmass we have shows evidence of really widespread volcanism. A lot of this stuff, this black volcanic rock, which is basalt, has covered enormous swaths of a lot of areas, like the Pilbara in Western Australia. But not only that, some of the rocks we have erupting were much, much hotter than basalt. And in fact, they must have come from a much hotter mantle, so the interior of the Earth would have been hotter back then too. And it formed things like these weird spinifex-y olivines that we see that only grow in magmas that are much hotter than your present-day basalt. So this tells us two things. One, volcanoes came back with a vengeance at this time. Now, whether it was due to something tectonic or just a build-up of heat in the interior is unclear, but certainly this amount of volcanism would have pumped a lot of CO2 into the atmosphere, and we would expect things like global ice ages and whatnot to not be apparent, and that's what we see. We see a heavy CO2 atmosphere, no evidence of ice anywhere, and huge amounts of volcanism over most of the surface of the Earth. Things are about to get a little complicated though, so we'll move up a little bit and see what the aftermath of this event was like. Right here, we're at about 2.4 billion years ago, almost halfway through Earth's history. Now, the interesting thing, as I mentioned earlier, to Earth's atmosphere before this period was that there was no oxygen. And this is kind of curious because we did have photosynthesis appearing 3.5 billion years ago, almost a block away now. So why did photosynthesis take so long to build up oxygen in the atmosphere to any decent level where we can see it. Part of the reason for that was probably volcanism. We had a lot of volcanic gases being poured out. Some of them are quite reducing, like methane. They react with oxygen in the atmosphere. And as a result of having no oxygen around, we form very different minerals on the surface to what we see today. Now, this is an example of that. This is known as a banded iron formation, or in geology, you just call it a biff. And there's old geology jokes about bringing back the biff. But nevertheless, this is an iron ore. If you go to the Hamersley in Western Australia, this is what's being mined, which makes me cry a little bit every time inside when I think of this beautiful rock being crushed and molten down to steel. But this doesn't form anymore. It's not formed much for the last 2.5 billion years. And the reason is it requires an ocean that's saturated in iron. Now, the moment you get any oxygen in the ocean, it absorbs the iron drops out. You don't have much iron in the ocean anymore. Back before 2.4 billion years ago, you had no oxygen really, no free oxygen to react with the iron. The iron levels in the ocean would have built up. In fact, this even changes the color of the ocean. The oceans would have been a really kind of paley green color with this much iron dissolved in them. Now, any little whiffs of oxygen that were around caused the iron to precipitate out and form these banded iron formations. These beautiful red patterning are basically iron oxides in there. These only form in low oxygen environments though, where the iron in the ocean can build up. Ever since 2.4, we haven't formed these. Instead, we form things like what we call red beds, which if you ever go to Central Australia, you see the red dirt out there, it's all iron ore. That sort of stuff forms today, and if you were to crush that down and make a sedimentary rock out of it, you call it a red bed. So we find this highly oxidized surface from 2.4 on. Prior to that, we have these sorts of things taking up the iron, which require a really reduced ocean, very low oxygen environment. Now, that seems to be associated now with oxygen building up and things like volcanic inputs to the atmosphere dying down, which allows the oxygen to build up. And that causes something very peculiar, which happens just up here. So now we're at about 2.4 to 2.2 billion years ago. And this is the first evidence we have on the Earth of glaciations covering the entire Earth. This was a Snowball Earth event. Now, we had little hints of glacial rocks earlier on, but they weren't that widespread. This is the first time in the record where it seemed like the Earth very much froze over. Now, how we tell that is we have samples of rocks from that period, and this particular rock formed in a deep sea environment. It's a very fine sediment, and what you see in this rock are these big chunks. This formed probably 100 k's out to sea, and then we have this massive pebbles being dropped in them. Now, the only way to get pebbles from a landmass 100 k's out to sea today is when an ice sheet comes by, it grinds the crust up underneath, forms these pebbles, it carries it with it in the form of icebergs and drops them out into the ocean. So, these rocks we see everywhere at 2.4, including in areas we know were near the equator. We know that because the rocks preserve the magnetic fields as well, and we can tell from the direction of the magnetic field what latitude we're at. If we're near the poles, the magnetic field goes straight up and down. If we're at the equator, the magnetic field goes horizontally. So if you have a record of that trapped in the rocks, you can look at the magnetic field, you can see the evidence for ice in these drop stones. Geologists are very creative on name features. So this is a stone, and it dropped into the sediment, hence drop stone. So we're a very predictable bunch. Anyway, this is a drop stone, and it formed in a rock that was near the equator at the time, which means the entire Earth froze over during this interval. Now, why did the Earth freeze over now? Now, as I mentioned, oxygen had slowly built up by this point, and that's probably associated with a decrease in volcanism just now. In fact, some crazy people, i.e. me and my co-authors, have argued there's actually a volcano vacation during this interval. It's a very, very distinct period in Earth's history where we see very low levels of volcanism. Now, maybe the Earth overshot itself, 2.7. There was a lot of volcanism back there. It's very subdued at this period of time, and this gave the opportunity for not only oxygen levels to build up, but CO2 from volcanoes wasn't as extreme, and as a result, the Earth dropped into a frozen state during this time period. It didn't last for long, or it lasted for a couple of 100 million years, but it came out of it by about 2.1 million years where we start to see lots of volcanism occurring again. All right, we'll continue up this way now. Alright, so at this point here, we've exited the Archean back there, near where the global Snowball Earth event was, and we've entered into a period of Earth's history known as the Proterozoic. Now, at this point here, we're at about 1.8 billion years ago, the beginning of a period in the Proterozoic of extreme climatic stability where not a lot seemed to happen on the surface of the Earth. This has been called by some workers the boring billion. So from 1.8 billion years ago to 800 million years ago, there's about a billion years of Earth's history where geology kind of happened, but not very fast. The surface environment didn't change very much. Evolution didn't really seem to do very much either. It was a very stable, very quiet environment where not a lot happened. So we're going to leapfrog through this billion years because there's not an awful lot to talk about and head down towards the Proterozoic where it starts getting busy again. Are you still recording?
Of course.
You're recording all this boring stuff.
Sorry.
So we're in the boring bit right now. We're about halfway through it, and as you can see, it's been remarkably boring. We're past the science buildings down there now. We're in the middle of the campus, which is lots of lecture halls and accounting and finance and stuff. So very appropriately the boring bit. But it's kind of interesting in its own way in that, the Earth's history up until this point has been one of dramatic change the entire way through. Things have always changed. It's been evolving. To have a billion years of Earth's history where not much has happened, I think is kind of interesting in itself. And no one's quite explained why the Earth was quite so stable for quite so long. Let's carry on, and we're about to get slightly less boring soon. If you get bored with the boring bee and the coffee carts, just over there. I was still in the boring bin at this point, but at least one slightly interesting thing has happened. And so we're at about 1.2 to 1.1 billion years ago now, and all the continents of the Earth actually came together to form a supercontinent known as Rodinia. Now, we've had hints of a supercontinent before this, but there's not enough for us to really tell. Here it's very obvious that most of the continents that exist today were actually stuck together in this giant supercontinent. Now, why this is cool for us is that a number of continents came together at this period and stayed together at the core of Rodinia. This included Australia, Antarctica, Africa, India, Madagascar, South America. The core of a bunch of continents, which would later on be known as Gondwana, actually came together here. And they stayed together for an enormously long period of time now, all the way to the breakup of Gondwana, which literally just finished up about 100 million years ago or so. So, all of that evolutionary history, the shared history of Gondwana, the animals we share, the plants, marsupials, that all began around here at about 1.2 billion years ago with the formation of Rodinia. Alright, let's move out of the boring bit. Alright, the boring being just ended very, very spectacularly right at this period here with the Snowball Earth event. So we're entering in a period between about 700 to 600 million years ago known as the Triassic. The Earth went into two major glaciations at this period, the Mariner and the Sturgeon glaciations. And at that time, it nearly seemed to have entirely frozen over. Now, the evidence we have of these glaciations comes largely from rocks exactly like this. This came from the Cryogenian in South Australia, and in fact, the first evidence for Snowball Earth theory came from these South Australian rocks. These have been studied for a long time. They're at the equator during this time period, and they have these dramatic drop stones in them, which tells us that there were widespread ice sheets and icebergs actually at the equator during this period. Now, this was a really interesting period in Earth's history. For some reason, the Earth got cold enough that it froze over. So either we're thinking about low CO2 gas levels to enable the glaciation to start, and then once it starts growing, the ice sheets start growing, they reflect more light, they cool the Earth down even further, and the end result is a Snowball Earth event. Now, it takes a long time then for volcanoes to bring those CO2 levels back up to the point where they can actually get out of the Snowball Earth event, on the order of 50 to 100 million years. That eventually happens, but as you can imagine, that puts an enormous stress on the ecosystems around at the time, the life forms that are around. So after a period of about 1 billion years of not having to really try that hard, suddenly they're faced with some of the worst disasters life has ever had to deal with, dealing with 100 million years of fully frozen Snowball Earth. Life scraped through, and after it did, it came back with some serious innovations. So at this period here, from about 600 million years ago to the start of the Phanerozoic, about 530 million years ago, we're in a period of time known as the Ediacaran. Now, if you're in the northern hemisphere and you're from England, these rocks are still in what we call the Precambrian, they're a dead zone. We see all the animals that appear in life in these northern hemisphere rocks appearing at the start of the Cambrian. Life seems to explode onto the scene. And that's peculiar in itself. And it wasn't until people went to South Australia and started looking at some of the rocks there, and they realized there were some very fine-grained rocks like muds that preserved the fossils of some really amazingly soft-bodied creatures in them. And these are now known as the Ediacaran fauna, after the area in South Australia where they were first found. They're bizarre. We do argue about exactly what they were. For many years, people thought these were an entirely different kingdom of life, unrelated to modern animals. They were soft-bodied, they kind of looked jellyfish-like, they seemed to float around on the seafloor doing their own things. Some look like jellyfish, some look like sea feathers, others look like nothing we've ever seen. They don't share a lot of the symmetry a lot of the other animals have, so it's very unclear how they were related to animals for a very long time. These days, with modern genetics, using molecular evidence, we now think they're part of a larger group known as Cnidaria. And that includes corals today and jellyfish and things like that. So we think they were part of that group, but in a very ancient, archaic form. These guys floated around on the seafloor doing their thing for this Ediacaran period. They were very soft-bodied, so they're hard to preserve. You don't see many jellyfish fossils in the fossil record because they just get destroyed so easily. They don't have a hard shell. But since the Cryogenian all the way up to the Cambrian, life seems to have been, or these things seem to have been dominating the biosphere for most of that interval, doing their little hippie thing, floating around on the seafloor, taking life casually. But all that was about to change for them very dramatically in just a second. Okay, so right about this point here, we've just passed from the Proterozoic into the Phanerozoic. This is now the Cambrian period. And this is the explosion of life. Now, this is where these guys appear on the geological record. This is my personal favourite. This is a trilobite, of course. It's a hard-shelled arthropod related to other arthropods around today, like insects and crustaceans and stuff. Now, these guys were really distinctive. They used to roll up in a little protective shell to protect themselves. Very big compound eyes they could see through. But they're just one example of this kind of explosion of life at this time. We still argue as to why the Cambrian explosion was so dramatic. Why did so much appear in the record then? The running theory is that there's a massive swash of nutrients and minerals into the oceans at this period due to the erosion of the Great Unconformity, which wiped off a lot of the continents and dumped all that nutrient into the ocean. And it made a lot of the minerals from which these animals make their shells available for the first time. So animals could grow big and diversify rapidly, and that's why we see such a proliferation of life at this interval. Whatever it was, the big adaptation that appeared in the Cambrian was hard shells. These guys had tough, hard outer shells. They were creating these in different ways. A lot of them were calcium carbonates, a lot of them were more organic compounds, chitin, but they all appeared on the record at this time. Now you imagine a trilobite or a crab up against our little blobby jellyfish friend, the Ediacara fauna. If these guys met in a fight, there's only one way that's going to go. This poor little guy's going to get torn to shreds. So a lot of the Ediacaran fauna that lived on the seafloor just got decimated once the animals appeared with their hard shells, their hard parts, their nippers, their claws. These guys really, this little poor Ediacaran really took a beating at that point in time. So it may have been an extinction event for the Ediacara, but it was an expansion for the animals and suddenly really appeared en masse at this time in the geological record. Let's move ahead quickly now to get through the Proterozoic. Sometimes you can't plant this stuff. You see, it just went from like dead ground to green ground. This, ironically, is right around 400 million years ago, which is right when we see the first appearance of land plants in the fossil record. Now, land plants have a bit of a challenge. They're not just growing in water. Water's not everywhere for them. The big challenge land plants have to overcome is getting water from the ground, from their root system, up to the top. The very first land plants that evolved had very, very limited ability to move water up. So we're talking about things like mosses and related plants today. They slowly got slightly bigger, up to maybe horsetails, and then they progressively evolved higher and higher through time as their vascular system evolved. So as their ability to transport water up the tree trunk and to their leaves at the end, as they got more and more advanced, plants would get bigger and bigger. But the first ones appeared here in the fossil record, and they were like little tiny mosses, and that's where land plants kicked off. Now if we move forward fairly fast now, right now we're into the Devonian, which is the time of the fishes, really. This was an enormous diversification in fish forms. Now, earlier on in the Devonian, most of the fish around that dominated the ecosystem of the oceans didn't look like present-day fishes. They were armored fishes called placoderms. These guys may have had fish-like bodies, but they had heavily armored heads. So they were like tanks of the sea. Some of these guys were truly terrifying. The largest known was 9 meters long. It's called Dunkleosteros. I'll put a picture of him up for you just so you see what he looks like. But he was horrifying that an animal like this ever existed. A 9-meter long armored fish with a mouth and a head that looked exactly like the xenomorph from Alien. You've seen the movie Alien? That's what he looked like, but 9 meters long. It was a thing of nightmares, and it worries me hugely that an animal like that ever evolved. But the placoderms have a limited time on the Earth. If you ever go to Canoundra in Western Australia, Western New South Wales, it's actually spelled Kenowindra, but they pronounce it Canoundra. There's an amazing fish museum there, and it's formed, the rocks there are right from the Devonian period, and it's when an old lake dried up, an enormous amount of placoderms got left there and then buried and fossilized. And so it's one of the best fish finds in the world from that period. So I hugely recommend going out to check out those fish fossils if you're ever out that way. But this period anyway was this period of armored fishes. Now they got outcompeted slowly. Not only did sharks and rays appear from about this point onwards, but so did rayfin fishes. Now rayfin fishes weren't as heavily armored as the armored placoderms, but they were light, they were fast, they were agile. If you've ever seen a tuna swim in the open ocean or a marlin, you appreciate just how unbelievably hydrodynamic these animals are. So these poor armored fishes didn't have a chance. They were big, they were tough, they could take a hit, but they were nowhere near as fast as the rayfin fishes. And eventually they were outcompeted in that same ecosystem niche by fish that were just faster and agile and could get to the prey much, much quicker than placoderms could. All right, let's move along quickly now. Right, at this point we've entered into the Carboniferous, which is a period known in the northern hemisphere as when most of the coal forms In the southern hemisphere, most of the coal forests form in the Permian, but this is when an awful lot of life proliferated in swamps, in forests. Now, I'm not carrying a piece of coal here at the moment because I didn't want to do a ScoMo in Parliament, but you can imagine what coal looks like. The entire Earth was covered in these peaty, swampy forests at the time. These were full of photosynthesizing plants. They pumped out an enormous amount of oxygen. Oxygen levels went through the roof. So we're talking over 30% atmospheric oxygen in this interval here. And this allowed some crazy things to happen. A lot of animals that kind of passively breathe via book lungs, like insects, could get to much, much bigger sizes. We're talking dragonflies with nearly 1 meter wingspan. We're talking millipedes 2 meters long. Some of these beasts were just crazy sizes. So insects and arthropods in general could get to much, much larger sizes. But it comes with a risk factor. 30% oxygen is highly, highly flammable. And a lot of these forests just got continually wiped out by raging wildfires all the time. So these are the forests that formed most of our coal deposits though. If we move through this quickly from the Carboniferous into the Permian, in the Permian, Pangea formed. The Earth got very dry, very hot, very arid in the inside. It was a tough place to live, but not quite as tough as right now. Here we're at a period where the Permian ends and the Triassic begins. This is the Permian-Triassic boundary. This is a ridiculous part of Earth's history where we see the largest mass extinction of all time. In fact, 96% of all life got wiped out right now. Life was unbelievably lucky to scrape through this one. 70% of land animals and 96% of all marine life just disappeared from the face of the planet. What caused this extinction, I hear you ask? This is the tricky thing. We don't know. There were things going on at the time. The Siberian traps in Siberia, a huge volcanic province, was erupting, but none of this was enough by itself to cause the scale of extinction we see. Something happened either in the oceans, perhaps overturning and releasing a whole bunch of gases that were trapped down there, or some other people have argued ice started to melt and release methane into the atmosphere. The long and the short of it is debated, and there's no clear answer as to what happened at this boundary to nearly wipe life off the face of the planet. All right, life scraped through. It did, and we're entering now a period known as the Triassic. Now, a lot of the stones that form around the Sydney Basin are from this period, and I was always disappointed as a little junior geologist when I was younger. Oh, no fossils in there. But of course, the Triassic, the first half of it, there are no fossils. But right around this time now, in about the middle Triassic, dinosaurs appear for the first time. And we start seeing them. They're about the size of chickens. Things like Eoraptor, when they first evolved, they get big very, very fast, and then they all went extinct, and then we're left with birds who are, again, the size of chickens. So it's a nice circle of life there. All right, we'll come down a little bit here. We've entered into the Jurassic at this period. So the time of the giant dinosaurs, we've got sauropods walking the face of the Earth, your Brachiosaurus, your Diplodocus, they all around in this period. So some of the most characteristic monsters of Earth's history, which is ironic because we're just outside the childcare centre here also. Characteristic, no. We're ending the Jurassic. We're now into the Cretaceous period here. Those are some of the hottest temperatures we ever saw. There was no ice on the surface of the Earth at this time. Proliferation of rainforest and those sort of environments. And if we come down towards the end of the Jurassic, which occurred just about here, we have the evolution of one of the most iconic apex predators of all time, which isn't just this guy. This is his tooth. This is the T-Rex's tooth. So T-Rex evolves right around now, about 67 million years ago. One of the most formidable apex predators of its time. Huge head, huge set of teeth. Could probably move, unlike what we originally thought. But an incredible apex predator found in the late Cretaceous. It evolved in the geological record. We see it for the first time right now. T-Rex just went extinct. That's the length of the reign of its history on the surface of the Earth. It's 65.5 million years ago. The Earth was hit by a meteorite. It formed a giant crater in the Yucatan Peninsula of Mexico called Chicxulub, and the scale of this event was enormous. It created tsunamis over 60 meters tall around the Caribbean. There was a huge violent event. It threw all this gas and dust into the atmosphere, which would have caused a nuclear winter for a while. The long and the short of this, most dinosaurs went extinct then, with the exception of course, the avians, the birds now. But this was largely the end of the dinosaurs' reign at this period just now. But T-Rex's reign is this tiny little window of time in this whole history of the world that we've just had. Now we're into the Paleogene, which is the time of the mammals. So we're moving, there's so much we could talk about here. The Paleogene, thermal maximum, we've got the Eocene, which is huge tropical rainforest, no ice caps. We had apes evolving around this time for the first time. We have some really archaic forms of mammals which never existed, don't exist now. Things like, if you want to have nightmares, Google Andrewsarchus. It's this giant 6-meter long werewolf of doom that stalked the forest at this point. We're going to move past all that because we're nearing our end here. Right around now, we get the apes finally evolving into something that starts looking fairly human-like, at least hominid. This is a very famous skull from a specimen known as Lucy. Lucy's from Africa. She was an Australopithecine afarensis. This is one of our earliest human ancestors. She would have stood about 1.5 meters high, so fairly short. But the interesting thing about Lucy is when you look at where her spine came out, it came out from the base of her skull, not the back like in most great apes. Lucy stood upright. She stood up with a skull like this. We're actually starting to see a lot of changes in Lucy too. Her brow ridges are less pronounced in a lot of apes. She's stopped getting this really slopey skull and starting to get a bit of a forehead curvature. And her dentition is completely different. Most great apes have very pronounced canines. Don't know why, they're not vampires. Gorillas don't need them to eat, but they have massive canines. Just an aggression thing, I suppose. But in humans, we lost a lot of this. As our brain cases got bigger, we couldn't have the strong jaw muscles affixed to it to kind of satisfy that same diet. We end up losing a lot of that dentition as well, lower scaled canines, and Lucy had that. Unfortunately for Lucy, she seemed to have died from a fall, so I guess going from tree climbing apes to being a hominid, Lucy came down to the tree pretty hard in the end. Let's move forward a little bit. So we've now reached around here, around 200,000 years ago, we start to see modern hominids appearing in the record. So 200,000 years ago, we see evidence of Neanderthals in Europe. There were Denisovans in the Asian side of Eurasia, and there are other hominid species evolving in Africa, which shortly after become modern humans and expand out of Africa. So I don't have any skull specimens for a Neanderthal, but if you want to see what one looked like, I'm about exactly the same height as your average male Neanderthal, and almost exactly the same weight. They're about 5'9", 5'10", about 90 kilos, so Neanderthal specimen. Anyway, from there to the out of Africa modern humans about 100,000 years ago, this was the population expansion that merged with Neanderthals eventually in Europe sometime later, moved through Australasia eventually and settled in Australia, and a lot of the indigenous populations of Australia stem from this third wave out of Africa. We move back a little bit from then. Right, we're up to modern humans now in Europe. They've inherited a bit of Neanderthal DNA on their way. We're about 30,000 years ago. 10,000 years ago is the dawn of agriculture, civilization. We see some of the earliest agricultural sites from around this period here. And the present day then, all of recorded history, which is 10,000 years ago to now, is about that far in our timeline here. So if we look back up the timeline to how far we've gone, the history of the Earth is that entire Wally's Walk we did, all of recorded human history is about that much. So we're outside the ancient history department right now. Everything that's preserved in that ancient history department, all of that recorded human history is this tiny little sliver of time compared to the absolute oceans of time that the Earth has been around for. So if you take nothing else from that crack, it's that the Earth's time is deep and very, very long compared to anything we think of as human timescales. And I think with that, I've definitely talked enough. I've got to let my poor people off the hook. So we'll see you back in the lab.
Perfect. Wait.